Hi there, I'm Sridhar Chandrasekaran, and I'm excited to share my knowledge and experience in transmission line construction with you. In this series, my goal is to equip engineers and managers with the essential know-how they need before stepping into the field and taking charge of their projects. We'll dive into everything from the basics of construction and execution planning to tendering, budgeting, and even touch on the engineering ethics that are so important in our profession. Each week, I'll be posting a new video. In each chapter, we'll explore relevant technical topics, discuss ethical considerations, and wrap up with a thought-provoking quote. So, stay tuned. There's a lot to cover. Disclaimer. Just a quick note. The content in these videos is meant for informational and basic educational purposes only. These videos aren't intended to provide professional advice or endorsements. This helps set the right expectations about the nature of what we're sharing, especially since we draw on material from various sources under the principle of fair use. In our previous chapters, Chapter 1 introduced the basics of electricity and provided a brief overview of transmission line construction. In Chapter 2, Part 1, we delved into the workings of generators and turbines, along with an examination of various thermal power generation methods such as coal, natural gas, and diesel power generation. In this chapter, we will complete our exploration of power generation by covering the remaining types of energy production, including nuclear power generation, various forms of renewable energy, and emerging technologies. This will give us a comprehensive understanding of how electricity is generated using different methods across the energy landscape. By the end of this chapter, we'll have a clearer picture of the technological advancements, environmental considerations, and energy efficiency of these power generation methods, providing valuable insight into the future of energy production. Having covered the types of fossil fuel power generation, let's now dive into the remaining types of power generation. This will help us complete our understanding of the various methods used to produce electricity, including nuclear power, renewable energy sources, and emerging technologies. Each of these methods plays a critical role in shaping the future of energy production, with a growing focus on sustainability and efficiency. The remaining types of power generation are as follows. 1. Nuclear power generation uses nuclear reactions, specifically nuclear fission, to generate heat, which is then used to produce steam that drives turbines to generate electricity. Nuclear power is known for its ability to generate large amounts of electricity with low greenhouse gas emissions, but comes with challenges like radioactive waste management and high upfront costs. 2. Renewable energy generation. There are 5 key types that we'll explore one by one. 1. Solar power, photovoltaic. PV. This method converts sunlight directly into electricity using photovoltaic cells made of semiconductor materials like silicon. When sunlight hits the cells, it excites electrons, generating an electric current. Concentrated solar power, CSP. CSP uses mirrors or lenses to concentrate sunlight onto a small area, heating a fluid that produces steam to drive turbines and generate electricity. 2. Wind power. Wind turbines capture the kinetic energy from wind and convert it into mechanical energy, which is then used to generate electricity. Wind farms, both onshore and offshore, are common installations to harness this renewable resource. 3. Hydropower. This method uses the energy from flowing water, typically through dams, to turn turbines and generate electricity. It is one of the oldest and most reliable forms of renewable energy. Run-of-the-river systems or reservoir-based systems are common approaches to hydropower generation. 4. Geothermal power. Geothermal energy taps into the heat from the Earth's interior. This heat is used to produce steam, which drives turbines connected to generators to produce electricity. Geothermal power plants are usually located in regions with high tectonic activity, where heat is closer to the Earth's surface. 5. Biomass power. Biomass power generation involves burning organic materials like wood, agricultural residues, or dedicated energy crops to generate heat. This heat is used to produce steam, which drives turbines to generate electricity. Biomass is considered renewable when the fuel sources are sustainably managed, as it can be continuously replenished. 6. Emerging methods of power generation. We have tidal and hydro. 1. Tidal and wave power harnesses energy from ocean tides and waves to generate electricity. These methods are still in the development phase, but have significant potential for renewable energy. 2. Hydrogen fuel cells uses hydrogen as a fuel source to generate electricity through an electrochemical reaction, emitting only water as a byproduct. Hydrogen fuel cells are gaining attention as a clean energy solution for the future. Each of these methods brings unique benefits and challenges, contributing to a diverse and evolving energy landscape. Let's now venture into nuclear power generation, a highly efficient method of producing electricity. Overview of nuclear power generation. Nuclear power generation relies on nuclear fission, a process where the nucleus of an atom is split into smaller parts, releasing a tremendous amount of energy in the form of heat. This heat is used to produce steam, which then drives turbines to generate electricity. Let's break down the working process into the following key components: source, nuclear fission, heat generation, heavy water, steam turbine, electricity generation, cooling systems, and safety systems. How nuclear power generation works. Nuclear reactor. In the nuclear reactor, the primary fuel used in nuclear reactors is typically uranium-235 or plutonium-239. Uranium is the most common choice, often enriched to increase the proportion of uranium-235, which is more reactive and capable of sustaining a chain reaction. The uranium fuel is shaped into small pellets, which are loaded into fuel rods and placed within the reactor core. Nuclear fission and heat generation. Nuclear fission occurs when a neutron collides with the nucleus of a uranium-235 atom, causing it to split into smaller atomic fragments. These splitting releases an enormous amount of energy in the form of heat, along with additional neutrons. The released neutrons go on to split other uranium atoms, creating a self-sustaining chain reaction that produces continuous energy. The energy released from fission reactions generates intense heat within the reactor core. This heat is transferred to a primary coolant, usually water or heavy water, which flows through the reactor core to absorb the generated heat. Heavy water and steam production. In certain reactors, heavy water D2O is used as a moderator and coolant. Heavy water contains deuterium, an isotope of hydrogen, which slows down the neutrons produced during fission. This slower movement allows neutrons to sustain the fission reaction efficiently, especially in reactors using natural unenriched uranium as fuel. This hot coolant transfers its heat to a secondary water system in a heat exchanger or steam generator, where the secondary water is turned into steam. The primary and secondary water systems are separated to prevent radiation from reaching the turbines. Steam production and turbine. Once the steam is produced by primary coolant in the reactor, the high-pressure steam flows through a series of turbines, causing them to rotate. These turbines are connected to a generator via a shaft, and the mechanical energy from the rotating turbine is used to produce electricity through electromagnetic induction. Electricity generation. The generator, powered by the rotating turbine, produces electricity through electromagnetic induction. This electricity is then sent to transformers, where the voltage is increased for efficient transmission across the power grid. Cooling system. After passing through the turbines, the steam is cooled and condensed back into water in a cooling system. The water is then returned to the reactor to be heated again, completing the cycle. The cooling process is facilitated by cooling towers or external water bodies, like rivers or seas, that help dissipate the heat. The condensate, now in liquid form, is returned to the reactor for reheating, completing the cycle. Effective cooling is essential for maintaining safe operating temperatures within the reactor and preventing overheating. Control rods. The reactor's fission process is controlled by control rods, made of materials like cadmium or boron. These rods absorb excess neutrons and help regulate the chain reaction, preventing the reactor from overheating. Safety systems control rods. Control rods made from materials like boron or cadmium absorb excess neutrons to regulate or halt the fission reaction. When inserted into the reactor core, they slow down or stop the chain reaction. Containment structure. Nuclear reactors are enclosed within a containment structure, a thick, reinforced concrete and steel shell designed to prevent the escape of radiation in the event of a malfunction. Emergency Core Cooling System, ECCS. In case of an emergency, such as overheating, the ECCS rapidly cools the reactor core, helping to avoid a meltdown. Radiation monitoring and shielding. Continuous monitoring systems are in place to detect radiation levels within and outside the plant. Shielding materials, such as lead and concrete, protect personnel and the environment from radiation exposure. Key features of nuclear power generation. Low emissions. Nuclear power plants do not emit greenhouse gases during operation, making them a clean energy source in terms of carbon emissions. High efficiency. Nuclear power is one of the most energy-dense forms of power generation, meaning a small amount of nuclear fuel can generate a large amount of electricity. Baseload power. Nuclear power plants provide a stable and continuous source of electricity, making them ideal for baseload power supply, meaning they can run constantly to meet the minimum demand. Challenges and considerations. Radioactive waste. One of the biggest challenges of nuclear power is the disposal of radioactive waste, which remains hazardous for thousands of years. Safe long-term storage solutions are essential. Nuclear accidents. While nuclear power is generally safe, accidents like Chernobyl and Fukushima have highlighted the potential risks of radiation leaks and environmental contamination. High initial costs. Building a nuclear power plant involves high capital investment and long construction times, though operational costs are relatively low. Fuel types. Uranium-235, the most commonly used fuel in nuclear reactors. It is enriched from natural uranium to increase its concentration for sustained nuclear reactions. Plutonium-239, also used in certain types of reactors and produced as a byproduct in uranium-fueled reactors. In conclusion, nuclear power is a highly efficient and low-emission source of electricity. Despite its challenges, such as waste disposal and potential risks, it remains a key component of the global energy mix, particularly for countries looking to reduce their carbon footprint while maintaining reliable, large-scale power generation. We are now beginning our exploration of renewable power generation methods, starting with hydropower generation. How it works. Hydropower is one of the oldest and most reliable forms of renewable energy. It harnesses the energy of flowing or falling water to generate electricity. The process typically involves using a dam to control the flow of water and convert the potential energy of stored water into mechanical energy, which is then transformed into electrical energy. Let us explore the type of hydropower generations. Steps in hydropower generation: water source and dam. The process starts with a water source, usually a river or reservoir. Dams are built to hold large quantities of water, creating a reservoir at a higher elevation. By storing water at a higher elevation, the dam creates potential energy due to gravity, water flow, and intake. When electricity generation is needed, gates in the dam open, allowing water to flow through intake pipes called penstocks. The water's flow is directed toward the turbines. The water gains kinetic energy as it flows through the penstock, increasing its velocity as it descends to lower levels. Turbine rotation. The fast-flowing water hits the blades of the turbine, causing it to spin. The turbine is similar to a large fan, and the mechanical rotation of its blades is powered by the moving water. The turbine's rotation converts the water's kinetic energy into mechanical energy. Electricity generation. The rotating turbine is connected to a generator via a shaft. As the turbine rotates, it spins the generator, which uses electromagnetic induction to produce electricity. Inside the generator, magnets and coils of wire move relative to one another, converting the mechanical energy from the turbine into electrical energy. Water release. After passing through the turbine, the water is discharged into a downstream tailrace or river. The water continues to flow naturally, unaffected by the electricity generation process. Transmission of electricity. The electricity generated by the turbines is transmitted to transformers, which step up the voltage for long-distance transmission via power lines to homes, businesses, and industries. Plutonium-239, also used in certain types of reactors and produced as a byproduct in uranium-fueled reactors. In conclusion, nuclear power is a highly efficient and low-emission source of electricity. Despite its challenges, such as waste disposal and potential risks, it remains a key component of the global energy mix, particularly for countries looking to reduce their carbon footprint while maintaining reliable, large-scale power generation. Types of hydropower plants. Impoundment, reservoir-based, hydropower. This is the most common type of hydropower. A large dam is built across a river to create a reservoir. Water is stored and released to generate electricity as needed. Second is run-of-the-river hydropower. In this system, water is diverted from a river without the need for large dams or reservoirs. It uses the natural flow of the river to generate electricity, but is subject to seasonal flow variations. Third is pumped storage hydropower. This is a type of hydropower that works as an energy storage system. Water is pumped from a lower reservoir to a higher reservoir during periods of low electricity demand, using excess electricity. During peak demand, the stored water is released back down to generate electricity, similar to a conventional hydropower system. Now let us know the advantages of hydropower, renewable energy source. Hydropower relies on the natural water cycle, making it a renewable and sustainable source of energy. Reliable and efficient, hydropower plants can operate continuously and provide consistent, reliable electricity. They have long lifespans and very high energy conversion efficiency. Low greenhouse gas emissions. Unlike fossil fuel-based power plants, hydropower does not produce direct greenhouse gas emissions during operation. Quick startup. Hydropower plants can ramp up production quickly, making them excellent for balancing fluctuations in electricity demand or supplementing other power sources. And the challenges of hydropower are environmental impact. Dams and reservoirs can disrupt ecosystems, affecting fish migration, water quality, and habitats for aquatic and terrestrial life. Changes in water flow can also affect downstream ecosystems. High initial cost. Building dams and associated infrastructure requires significant upfront investment. Geographic limitations. Hydropower is dependent on suitable geographic locations with sufficient water flow and elevation changes. It is not viable in flat or dry regions. In conclusion, hydropower is a reliable, efficient, and renewable form of energy that has been used for centuries. It plays a vital role in providing baseload power and helping to meet peak electricity demands. However, it requires careful environmental and social management due to the potential impacts on ecosystems and communities. In renewable energy, solar power generation plays a crucial role, second to hydropower generation. Despite the challenges of high initial setup costs and certain limitations in efficiency, solar power remains a key part of the future of energy generation. Here are some of the main types of solar power generation. 1. Concentrated solar power, CSP. 2nd, photovoltaic, PV, power generation. 3rd, floating photovoltaic, FPV, power generation. 4th, building integrated photovoltaics, BIPV. These methods represent various ways solar energy is harnessed, each with its unique applications and advantages. Let us first explore concentrated solar power. Solar thermal systems focus sunlight to generate high temperatures, which produce steam that drives a turbine connected to a generator. Concentrating solar energy. Solar collectors. Solar thermal systems use mirrors or lenses to concentrate sunlight onto a focal point or onto pipes that carry a heat transfer fluid. There are several types of solar collectors, including parabolic troughs, curved mirrors, focus sunlight onto a tube containing a heat transfer fluid, typically synthetic oil, that runs along the focal line of the trough. Solar power towers. Thousands of flat mirrors called heliostats track the sun and focus sunlight onto a central receiver on top of a tower. This receiver contains a heat transfer fluid, often molten salt. Parabolic dishes. Parabolic dishes focus sunlight onto a single point, usually with a Stirling engine to convert heat directly into mechanical energy. Linear Fresnel reflectors. Flat mirrors arranged in rows focus sunlight onto tubes containing fluid. These systems are simpler and less costly, but are generally less efficient. Heat transfer and storage. Heat transfer. Fluid. The heat transfer fluid, often synthetic oil or molten salt, absorbs the concentrated solar energy, reaching temperatures of 300 to 1000 degrees Celsius, 572 to 1832 degrees Fahrenheit, depending on the technology. Thermal energy storage. Some systems use molten salt as a storage medium. The heated salt can store energy for later use, allowing the plant to continue producing electricity even when the sun isn't shining, e.g., during cloudy periods or at night. This makes solar thermal power more flexible and reliable than traditional solar PV systems. Steam generation. The heat transfer fluid, after absorbing solar energy, is circulated through a heat exchanger or steam generator, where it transfers its heat to water. The water is converted into high-pressure steam, which is then directed to a turbine. This process is similar to traditional thermal power plants, like coal or natural gas, except that solar energy is the heat source. Turbine and generator operation. Turbine rotation. The high-pressure steam flows through a turbine, causing it to spin. This converts the thermal energy from the steam into mechanical energy. Electric generator. The turbine is connected to a generator via a shaft. As the turbine rotates, it drives the generator, converting the mechanical energy into electrical energy through electromagnetic induction. Electricity production. The generated electricity is then stepped up to a higher voltage using transformers and fed into the power grid for distribution. In summary, solar thermal power generation uses concentrated sunlight to produce heat, which is then converted into electricity via a turbine and generator system. By incorporating thermal storage systems, solar thermal plants can offer more reliable power than traditional solar PV, making them a valuable, renewable energy source in sunny regions. This technology combines renewable energy with the scalability and flexibility of traditional thermal power plants, contributing to cleaner energy production on a larger scale. Next is solar photovoltaic power generation. It involves converting sunlight directly into electricity using solar cells made from semiconductor materials. This process, known as the photovoltaic effect, does not rely on any moving parts or the production of heat, making it a clean and efficient way to generate electricity from the sun. Solar panels and solar cells. Solar panels. Solar panels consist of multiple solar cells connected together. Each cell is made from semiconductor materials, typically silicon, which have special properties that allow them to convert light energy into electrical energy. Solar cells. A solar cell is the fundamental building block of a solar panel. It contains layers of silicon, which are specially treated or doped with other elements to create an electric field across the cell. Photovoltaic effect. Absorption of sunlight. When sunlight hits the surface of the solar cell, the energy from the light, in the form of photons, is absorbed by the silicon atoms in the cell. Electron excitation. The energy from the photons excites electrons in the silicon atoms, knocking them loose from their atoms and allowing them to move freely. This movement of electrons is the basis for creating an electric current. Creation of electric field. The solar cell is designed with a positive and a negative layer, forming an electric field. This electric field forces the free electrons to move in a specific direction, creating a flow of electrical current. Electricity generation. Flow of current. As the electrons move, they flow through the electrical circuit created within the solar cell. This flow of electrons generates direct current DC electricity. Connection to other cells. Each solar cell generates a small amount of electricity on its own. To produce a usable amount of power, multiple cells are connected together within a panel. These panels can then be connected to form larger solar arrays to generate more electricity. Conversion to usable electricity. Inverter. The DC electricity generated by the solar panels is not compatible with most household appliances, which require alternating current, AC power. An inverter is used to convert the DC electricity into AC electricity so it can be used in homes, businesses, or fed into the power grid. Grid connection. In grid-connected systems, the AC electricity from the inverter is fed directly into the electrical grid, where it can be distributed to other users. In standalone or off-grid systems, the electricity is often stored in batteries for later use. In summary, solar photovoltaic (PV) power generation converts sunlight directly into electricity using the photovoltaic effect. Solar cells within the panels absorb sunlight, freeing electrons and creating an electric current that is converted to AC power via an inverter for use in homes, businesses, or the electrical grid. Wind power generation converts the kinetic energy from the wind into electrical energy using wind turbines. It's a clean, renewable energy source that has become increasingly popular due to its low environmental impact and sustainability. Wind turbine structure. Rotor blades. Wind turbines have large blades, typically 3, that are attached to a central rotor. The rotor blades are designed to capture the energy from the wind and are usually positioned high above the ground, where wind speeds are faster and more consistent. Nacelle. The nacelle is the housing at the top of the turbine tower that contains the generator, gearbox, and other essential components. It also supports the rotor blades and allows them to pivot or yaw to face the wind. Tower. The tower supports the nacelle and blades and elevates them to capture stronger winds. Towers can be up to 80 to 120 meters, 260 to 390 feet, tall for large-scale turbines. Yaw system. This system allows the nacelle to rotate and adjust the direction of the rotor blades to face the wind, optimizing energy capture. Capturing wind energy. Blade rotation. As the wind blows, it passes over the rotor blades. The blades are shaped like an airfoil, similar to airplane wings, causing a pressure difference on either side of the blades as the wind moves past. This difference in pressure creates lift, which causes the rotor blades to spin. Kinetic to mechanical energy. The spinning of the rotor blades converts the wind's kinetic energy into rotational mechanical energy. The speed of the blades is relatively slow, but the torque generated is high. Transmission through the gearbox. Gearbox. In most wind turbines, the low-speed rotation of the blades is connected to a gearbox that increases the rotational speed. This step up in speed is necessary to reach the thousands of revolutions per minute, RPM, needed to generate electricity efficiently in the generator. Direct drive turbines. Some modern wind turbines are direct drive and do not use a gearbox. Instead, they use a larger generator designed to operate at lower rotational speeds, which reduces maintenance and improves reliability. Electricity generation in the generator. Generator The high-speed rotation from the gearbox, or directly from the rotor in direct drive turbines, is transferred to a generator, typically located within the nacelle. Electromagnetic induction. Inside the generator, the rotating rotor spins within a magnetic field, inducing an electric current in the stationary coils, stator. This process converts the mechanical energy from the spinning blades into electrical energy. Type of current. The generated electricity is typically alternating current, AC, which is compatible with the electrical grid. Voltage conversion and grid connection. Transformer. The electricity produced by the generator is usually at a lower voltage. A transformer, often located at the base of the turbine tower, steps up the voltage for efficient transmission. Grid connection. The electricity is then sent through cables to a substation, where it is further transformed to the required voltage level and connected to the power grid for distribution to homes, businesses, and industries. In summary, wind power generation works by capturing the kinetic energy of the wind with turbine blades, which spin and drive a generator to produce electricity. Wind energy is a clean, renewable source that can significantly contribute to a sustainable energy mix. Biomass power generation involves converting organic materials, known as biomass, into electricity. Biomass can include wood, agricultural residues, animal waste, and other organic matter. This process is renewable as plants absorb carbon dioxide during growth, offsetting the CO2 released when the biomass is burned. Collection and preparation of biomass. Types of biomass. Common sources include wood chips, crop residues like corn stalks and rice husks, animal manure, and even municipal waste. Some power plants also use dedicated energy crops, such as switchgrass and fast-growing trees like willow and poplar. Biomass processing. Biomass is usually collected and processed to make it suitable for energy production. Processing may involve drying, shredding, or pelletizing to improve combustion efficiency. In some cases, biomass is transported to the power plant in a processed form, like wood pellets or briquettes. Conversion technologies. There are several methods to convert biomass into electricity. The choice of technology depends on the type of biomass and the scale of power generation required. The main conversion methods are direct combustion. Biomass is burned in a boiler to produce steam, which drives a turbine connected to a generator, producing electricity. This is similar to coal-fired power generation, but uses organic materials as the fuel source. Gasification. Biomass is heated at high temperatures in a low-oxygen environment, producing a gas mixture called syngas, hydrogen, carbon monoxide, and methane. This syngas can be used to power a gas turbine or burned in a boiler to generate steam. Anaerobic digestion. Biomass, particularly wet organic waste like animal manure or food scraps, is broken down by bacteria in an oxygen-free environment. This process produces biogas, mainly methane and carbon dioxide, which can be burned to generate electricity. Pyrolysis. Biomass is heated in the absence of oxygen, breaking it down into bio-oil, biochar, and syngas. The bio-oil and syngas can be used for electricity generation, while biochar can be used as a soil amendment. Electricity generation process combustion. Boiler system. In direct combustion systems, the processed biomass is fed into a boiler, where it is burned to produce heat. This heat converts water in the boiler into high-pressure steam. Turbine and generator. The steam generated by the boiler flows through a steam turbine, causing it to spin. The turbine is connected to a generator, which converts the mechanical energy from the turbine into electrical energy. Gas turbines. For gasification or biogas systems, the produced gas is used to fuel a gas turbine or an internal combustion engine. This drives a generator to produce electricity. In summary, biomass power generation involves burning or processing organic materials to produce heat, which is used to generate steam and drive a turbine connected to an electric generator. Geothermal power generation harnesses heat from the Earth's interior to produce electricity. This process takes advantage of naturally occurring heat stored within the Earth's crust, which can be accessed by drilling into geothermal reservoirs. Locating geothermal resources. Geothermal reservoirs. Geothermal energy is often found near tectonic plate boundaries, volcanic regions, or areas with hot springs or geysers. These areas have geothermal reservoirs containing steam, hot water, or high-temperature rocks. Exploration and drilling. Geothermal exploration involves geological surveys, mapping, and drilling test wells to confirm the presence of geothermal resources. Once a suitable site is identified, production wells are drilled to access the geothermal fluid or steam. Types of geothermal power plants. There are three main types of geothermal power plants, each designed to accommodate different types of geothermal resources. Dry steam plants. These are the oldest type of geothermal power plant. They use steam directly from geothermal reservoirs to turn a turbine. This method is used where natural underground steam is available, such as at the geysers in California. Flash steam plants. The most common type, flash steam plants, use high-pressure hot water from geothermal reservoirs. As the water reaches the surface, it rapidly flashes into steam due to the pressure drop. This steam is then used to drive a turbine. Binary cycle plants. Binary cycle plants use moderate-temperature geothermal resources. Instead of directly using the geothermal fluid, it heats a secondary fluid with a lower boiling point, such as isobutane or pentane. The secondary fluid vaporizes and drives a turbine, while the geothermal fluid is re-injected into the ground. Heat extraction and steam production. Wells. In flash steam and dry steam plants, hot water or steam is brought to the surface through production wells. For binary cycle plants, hot water is pumped through a heat exchanger, transferring heat to a secondary fluid. Flashing process. In flash steam plants, the high-pressure hot water is released into a low-pressure chamber. Here, some of the water rapidly flashes into steam, which is then directed to the turbine. Turbine and generator operation steam to turbine. In dry steam and flash steam plants, the steam flows through a turbine, causing it to spin. In binary cycle plants, the vaporized secondary fluid drives the turbine. Generator. The turbine is connected to a generator by a shaft. As the turbine spins, it turns the generator's rotor, producing electricity through electromagnetic induction. In summary, geothermal power generation harnesses the heat from the Earth's interior to produce electricity. This renewable energy source is extracted from naturally occurring hot water reservoirs, steam, or heat within the Earth. The three main methods for converting this geothermal heat into electricity which we have explored. Geological surveys, like the one shown in the illustration, are used to identify the most promising locations for geothermal plants by analyzing surface temperature anomalies, volcanic activity, and fault lines. Geothermal power is a reliable and sustainable energy source with minimal greenhouse gas emissions, making it a valuable addition to renewable energy portfolios. Hydrogen power generation uses hydrogen as a fuel to produce electricity, typically through a process called fuel cell technology. This method is clean, efficient, and produces only water and heat as byproducts, making it an attractive renewable energy option. Hydrogen can be generated from a variety of sources, including water, natural gas, and biomass. Production of hydrogen fuel electrolysis. Hydrogen can be produced by splitting water, H2O, into hydrogen, H2, and oxygen, O2, through a process called electrolysis. In this method, an electric current is passed through water, separating it into its component gases. If renewable electricity is used, the process is emissions-free. Steam methane reforming, SMR. Currently, most hydrogen is produced from natural gas in a process called steam methane reforming. This process generates hydrogen and carbon dioxide, CO2. While SMR is efficient, it produces CO2 emissions, which need to be captured and stored for a cleaner process. Biomass gasification. Hydrogen can also be produced from organic materials through gasification. Biomass is heated in a low-oxygen environment, producing hydrogen-rich syngas, a mixture of hydrogen, carbon monoxide, and other gases. This gas can then be processed to extract pure hydrogen. Other sources. Some experimental methods for producing hydrogen include thermochemical processes driven by solar heat and photobiological processes using algae or bacteria. Storage and transportation. Compressed hydrogen. Hydrogen gas is often compressed and stored in high-pressure tanks for transport and use in power generation. Liquid hydrogen. For certain applications, hydrogen can be liquefied by cooling it to extremely low temperatures, -253 degrees Celsius or -423 degrees Fahrenheit. Liquid hydrogen is dense and more energy efficient for transportation, but it requires significant energy to cool and store. Hydrogen carriers. In some cases, hydrogen is stored in a chemical compound, such as ammonia or methanol, or in metal hydrides, which can release hydrogen when needed. These methods provide alternative ways to store and transport hydrogen safely. Fuel cells. Converting hydrogen to electricity. Fuel cell structure. A fuel cell consists of two electrodes, anode and cathode, separated by an electrolyte. Hydrogen is introduced at the anode, while oxygen, often from the air, is introduced at the cathode. Electrochemical reaction. The fuel cell uses an electrochemical process, rather than combustion, to produce electricity. At the anode, hydrogen molecules are split into protons and electrons. The protons pass through the electrolyte to the cathode, while the electrons are forced through an external circuit, generating electricity. Recombination at the cathode. At the cathode, the protons and electrons recombine with oxygen to form water, H2O, and release heat. This process produces only water and heat as byproducts, making it a clean form of power generation. Types of fuel cells. There are several types of fuel cells, each suited to different applications and operating conditions. Proton exchange membrane fuel cells, PEMFC. These operate at lower temperatures and are commonly used in vehicles and backup power systems. PEMFCs are efficient and have a fast startup time. Solid oxide fuel cells, SOFC. These operate at high temperatures, 600 to 1000 degrees Celsius, and are suitable for stationary power generation. SOFCs can use a variety of fuels, including hydrogen, natural gas, and biogas. Alkaline fuel cells, AFC. These were one of the first types of fuel cells developed and are used in space missions. They operate at relatively low temperatures and are very efficient but sensitive to impurities. Molten carbonate fuel cells, MCFC. Operating at high temperatures, MCFCs are suitable for large-scale stationary power plants. They can use natural gas and other hydrocarbons in addition to hydrogen. Electricity generation and power output. Direct current, DC. Output. Fuel cells produce direct current, DC, electricity, which can be used directly in certain applications or converted to alternating current, AC, using an inverter for general use. Stacking fuel cells. To generate more power, individual fuel cells are often stacked together in a fuel cell stack. The output depends on the size of the stack and the type of fuel cell, allowing for applications ranging from small portable devices to large power plants. Combined heat and power, CHP. Cogeneration. Fuel cells generate heat as a byproduct of the electricity generation process. In combined heat and power, CHP systems, this waste heat is captured and used for heating water or buildings, increasing overall efficiency. Thermal energy utilization. In larger installations, the thermal energy can be used for industrial processes, space heating, or even in absorption chillers for cooling, making fuel cell systems more versatile. In summary, hydrogen power generation uses hydrogen fuel cells to produce electricity through an electrochemical process that is clean and efficient. Hydrogen can be generated from various sources, including water, natural gas, and biomass, and when produced using renewable energy, it is a zero-emission solution. Tidal and wave power generation harness the natural movement of ocean water to produce electricity. Both methods are forms of marine energy that utilize the mechanical energy in water movements, but they capture energy from different sources. Tidal energy comes from the regular rise and fall of sea levels, while wave energy is generated by the movement of the ocean's surface. Tidal power generation. Tidal power generation relies on the gravitational pull of the moon and the sun, which causes periodic rises and falls in sea levels. These movements create predictable, renewable energy sources. Types of tidal power systems. Tidal barrages. A tidal barrage is a dam built across the entrance of a tidal basin. As the tide rises and falls, water flows in and out of the basin through turbines within the barrage, generating electricity. Tidal barrages take advantage of the difference in height, called the tidal range, between high and low tides. Tidal stream generators. These systems are similar to underwater wind turbines. Tidal stream generators are placed in fast-moving tidal currents, where the flow of water rotates the turbine blades, driving a generator to produce electricity. This method is less invasive than a barrage and can be used in narrow channels with strong tidal currents. Dynamic tidal power, DTP. This is a less common and experimental technology that involves constructing long dams extending out from the coast into the ocean. DTP aims to create artificial tidal currents, which can then be used to generate power. Wave power generation. Wave power captures energy from the surface motion of ocean waves. The energy in waves is generated by the wind blowing over the surface of the ocean, transferring kinetic energy to the water. Types of wave power systems. Point absorbers. These are floating structures anchored to the sea floor. As waves move past, They cause the structure to rise and fall. This motion drives a hydraulic or mechanical system, which in turn powers a generator. Oscillating water columns. This technology uses the up and down movement of water within a partially submerged chamber. As waves enter the chamber, they push air through a turbine, generating electricity. As the wave recedes, air is drawn back through the turbine, continuing power generation. Attenuators. These are long floating devices aligned parallel to the direction of the waves. The device consists of connected sections that flex as waves pass, creating a mechanical motion that drives hydraulic pumps, which then generate electricity. Overtopping devices. These devices capture waves in reservoirs above sea level. The stored water is then released, flowing through turbines to generate electricity. They function similarly to tidal barrages, but rely on wave action instead of tidal changes. In summary, both tidal and wave power represent sustainable, renewable sources of energy that utilize the natural movement of ocean water. Tidal power is generated by the predictable rise and fall of tides, while wave power captures the energy from ocean surface waves. Each has its advantages and challenges, but together they offer promising solutions for reducing dependence on fossil fuels and contributing to a cleaner, more sustainable energy mix. While these technologies are still developing, they have the potential to play a significant role in future renewable energy strategies, especially for coastal regions. In this chapter, we covered the following key topics in power generation. Nuclear power generation. We explored how nuclear energy is generated through the process of nuclear fission, using the heat produced to drive turbines for electricity production. Renewable power generation. Solar power generation. Converting sunlight into electricity via photovoltaic cells and solar thermal systems. Wind power generation. Harnessing the kinetic energy of wind through wind turbines to produce electrical power. Hydropower generation. Using the flow of water to generate electricity through hydropower plants. Geothermal power generation. Leveraging heat from the Earth's core to produce steam, which drives turbines. Biomass power generation. Converting organic materials into electricity through methods such as combustion and anaerobic digestion. Emerging methods. Hydrogen fuel cells. Generating electricity through electrochemical reactions in fuel cells using hydrogen as fuel with water as the only byproduct. Tidal and wave energy. Capturing energy from ocean tides and surface waves for power generation. With this, we have completed our study on power generation. In the next chapter, we will explore the requirements and prerequisites for starting transmission line construction, setting the foundation for the next stage of our learning. As we progress through our study program, we'll be emphasizing the importance of professional ethics by integrating key values at each step. Understanding what professional ethics entail and recognizing their significance are essential for us as professionals. These ethics guide our actions, ensure integrity, and foster trust in our careers, shaping not only our interactions, but also the impact we have in our respective fields. Professional ethics encompass the moral principles and standards that shape our conduct within our chosen professions. Typically outlined in a profession-specific code of ethics, these guidelines are designed to ensure that we act with integrity, responsibility, and respect in all our interactions, whether with clients, colleagues, or the broader community. By adhering to these ethical standards, we uphold the trust and credibility essential to our professional roles. Let's break down some key components. Integrity. Professionals should always act honestly and be truthful in their dealings. Avoiding deceptive practices and upholding fairness are essential. Confidentiality. As professionals, we often handle sensitive information. It's crucial to maintain confidentiality, ensuring that private data stays protected. Competence. Staying skilled and knowledgeable in our field is a must. This often means continuous learning and keeping up with the latest advancements. Responsibility. We have a duty to act in the best interests of our clients or the public, making sure our work does no harm and contributes positively to society. Respect. Ethical behavior also means treating everyone with dignity and respect, regardless of their background, status, or beliefs. Accountability. Finally, we must take responsibility for our actions and decisions, being ready to explain and justify them when needed. Competence in professional ethics refers to the responsibility of professionals to maintain the necessary skills, knowledge, and expertise to perform their duties effectively. Competence is essential for delivering high-quality work and ensuring that one's actions and decisions are reliable, safe, and beneficial to clients, colleagues, and the public. Continuous learning and skill development. Ongoing education. Competent professionals stay updated with the latest developments, techniques, and best practices in their field. This might involve attending workshops, conferences, training sessions, or pursuing advanced degrees and certifications. Adaptability. The ability to adapt to new tools, technologies, and industry trends is a key aspect of competence. Professionals should be willing to evolve and learn continuously to remain effective and relevant. Knowledge and expertise. Foundational knowledge. Professionals are expected to have a thorough understanding of the basic principles, theories, and practices in their field. Specialized expertise. Competence often includes gaining specialized knowledge in particular areas, allowing professionals to provide informed advice, solve problems, and contribute meaningfully to their field. Accuracy. A competent professional understands the importance of accuracy in their work. This means double-checking facts, calculations, or conclusions to ensure they meet industry standards. Practical experience, hands-on skills. Beyond theoretical knowledge, competence requires practical skills that are developed through experience. Professionals should seek opportunities to apply their knowledge in real-world settings, which enhances their ability to handle complex situations. Problem-solving abilities. Competent professionals possess strong problem-solving skills, enabling them to approach challenges logically, make informed decisions, and effectively address issues as they arise. Ethical decision-making. Informed judgments. Competence includes the ability to make sound judgments based on a thorough understanding of the situation, applicable laws, and ethical guidelines. Responsibility and accountability. Competent professionals understand their limitations and recognize when to seek additional expertise or refer a matter to a more qualified individual. They take responsibility for their work and hold themselves accountable for their actions and decisions. Commitment to high standards. Quality of work. Competent professionals strive to uphold the highest standards in their work, ensuring that it meets or exceeds industry requirements. Attention to detail. Competence involves being meticulous and attentive, as small oversights can lead to significant issues. Professionals should ensure that all aspects of their work reflect their commitment to quality and precision. Ethical and legal compliance. Adherence to standards. Competent professionals follow industry regulations, ethical codes, and legal requirements. This helps ensure that their work is safe, lawful, and ethical. Understanding of professional boundaries. Competence includes knowing one's limits and not undertaking work outside one's expertise. Competent professionals refer clients to other qualified individuals when necessary, demonstrating respect for the complexity of their field. Importance of competence in professional ethics: trust and credibility. Competence builds trust with clients, colleagues, and the public, as people are more likely to rely on and respect professionals who demonstrate high levels of skill and knowledge. Protection of stakeholders. Competent professionals help protect the safety, well-being, and interests of clients, organizations, and the public by making informed, responsible decisions. Contribution to professional integrity. By committing to competence, professionals uphold the integrity of their field. This fosters a positive reputation for the profession and reinforces ethical standards. In summary, competence in professional ethics encompasses a commitment to maintaining and enhancing the skills, knowledge, and expertise required to perform one's duties effectively. It involves continuous learning, practical experience, ethical decision-making, and adherence to high standards. By prioritizing competence, professionals build trust, protect those they serve, and contribute to the integrity and credibility of their profession. Today's quote is from John C. Maxwell. "A leader is one who knows the way, goes the way, and shows the way." This quote illustrates that a leader is someone who combines knowledge, action, and mentorship. They not only understand the path, but are committed to walking it and guiding others along it as well. By embodying these qualities, a leader earns trust and inspires those around them, creating a positive and effective environment for achieving shared goals. As we wrap up our session, I encourage you to subscribe and hit the bell icon so you won't miss any of our upcoming chapters. It's your gateway to mastering transmission line supervision. That brings us to the end of today's Chapter 2, concluding part on power generation. Next time, we'll dive into the fascinating topic of prerequisites for transmission line construction. Until then, take care, and thank you for watching.